If you're having problems with your images coming out and the color is just not quite right, maybe skin tones look a little too weird, a little too yellow or orange or blue, well, that's a white balance problem. And today, that's what we're going to take a look at. Hi, I'm Ryan Huffman, the photo professor, and I want to take a dive into understanding white balance today with you. But the first place we have to start is understanding how humans see color versus how cameras see color, so that you can have a fundamental understanding of color vision and how cameras and computers and even printers understand color, so we can kind of bridge that gap of knowledge. So one thing we need to understand is that not all light is created equal in terms of color. You can just see, I've set up this scene around me here to kind of demonstrate that a little bit. So right now over here we have a lot of window light coming in, and I've balanced that with a light source to illuminate my face that's the same color temperature as the window light. So this is kind of a whitish, coolish source of light. Behind me, you can see over to the side here, I have an incandescent bulb. So it appears kind of yellow. Up above, I have these lights that are actually relatively warm, also kind of yellowish, but they don't really appear so warm in this video, and we'll get to why that is. Behind my monitors, I have kind of a blue light that is just meant for an accent light, kind of something fun to just, throw some color in there. But you need to understand that all of these sources of light have different color temperatures. Okay, the way that we refer to color temperature is in a measurement called Kelvin. So we might have something that is, again, we'll start with the window light. The window light outside right now, it's about 1 o'clock in the afternoon. So that light is pretty close to being a pure white light. So we would, on the Kelvin scale, that would be right in the middle, what we'd call kind of a neutral color. So white, if it's pure white, that's a neutral color. It doesn't really have any tinge of actual color in it, like a blue or a yellow, etc. But as you can see over here with this incandescent bulb, it appears to be very warm, is what we would call it, because it is more of a yellowish or an orangish type of color. So that would be down on the spectrum in Kelvin. That's again what we would consider warm. That's going to be down around like a 2,000 to 3,000 Kelvin range. Whereas if we start getting into blue or cool color temperatures, not so much blue like we see behind the monitors. That's overtly blue. That's blue on purpose to be an accent light. But even let's say if the light that was coming in on this side of me, that it does appear kind of cool, but we just talked about that it's neutral. If it were to get more blue, like cloudy, settings, then that would be more up around like a 7, 8, 9,000 Kelvin, and that would be referred to as a cool color. So the warm colors are those that are down around like the yellowish and orangish range, down around, anywhere from 1,500 to 3,500 Kelvin. Cool colors are going to be up more around like 7,000 to 10,000 Kelvin. And the neutral color is going to be the white, where it's kind of right in between, somewhere around 5,000 to 5,500 Kelvin. So just understanding color temperature is really going to help. Here's where things get really fascinating. So I used to teach a color science course in college, and that course really focused on having students understanding the difference between how we see color and how input objects capture color, so like a camera, and then we see it on the screen when we bring it into a computer, and then how do we print it properly? Well, all of those different, input-output devices, they all see, perceive color differently. So we, human beings, the way we see color is in red, green, and blue. All right, so The sun or natural light emits these different wavelengths of color, red, green, and blue. We have cones in our eyes that perceive those wavelengths. So if we see something that is pure red, the reason why we perceive it to be red is because red, green, and blue wavelengths of light are hitting it. It's absorbing all of the green and blue wavelengths of light, reflecting the red wavelengths of light, and those wavelengths hit our cones and they stimulate the cone that sees red. It doesn't stimulate the cones that see green and blue. So when we are looking at objects and we're seeing color, it's because of whatever's being reflected off of it. We see different wavelengths of light either hitting an object, being reflected off of an object. And it's very interesting because our brain does this trick on us. It's called color adaptation or color constancy. Color constancy is what we really want to focus on here. Color constancy is basically telling us that our brain is discounting the illuminant. So what that means is that if you take just like a white piece of paper and you take a look at that white piece of paper under the current lighting conditions, or back here under this light or this light, if I weren't viewing lights really close to one another, that paper would appear to be white to me no matter what. So yes, you know, this light is pretty warm, pretty yellow, and it does appear kind of like a yellowish white right now. But your brain is basically telling you, look, it doesn't matter that it's under yellow light, the paper's still white. But that's not how cameras see it, because cameras don't have a brain, right? They have a computer chip, and the computer chip, you know, is just basically trying to tell the camera, okay, what is faithfully white? What is neutral? Okay, we're going to get to that in a second though. But our brains are just telling us constantly to discount whatever the illuminant is, whatever the color is of light that is hitting something, because our brains are telling us that color is a property of an object. So that's partially true, but the bigger truth is that color is actually the property of light in terms of how human beings see it. So here's a really easy experiment to prove this, okay? Take something, you know, I just have like this blue marker here. Take something kind of colorful, all right? Take it to a room where you can completely control the light. So like a basement would be ideal, but someplace where you can make the room completely dark if you needed to. So you're looking at this blue marker, and we can, you know, pretty much all agree that this is a blue marker. And even if I hold it under this light or that light, it's still blue, right? Because our brain is telling us that color is a property of the object. This marker possesses the color blue, all right? Now, in that room that you're in, turn the lights off. Now what color is the marker? Your brain wants to believe that the marker is still blue, but it's not. So, before you start filling my comments up with hate and say, how stupid are you? Of course it's blue. So this is proven. In fact, this little experiment we're doing here where you turn the lights off proves this in real time. It's a very simple scientific experiment. The only reason that human beings perceive any color whatsoever is because light waves, wavelengths of light, are hitting an object and reflecting back to our eyes, and then we perceive it as a certain color inside of our brain. We know that color is just a perception. It's not real because people experience color differently, right? Do you know anyone that has like a partial color blindness? They can't see reds maybe, or they can't perceive greens very well, you know, or a lot of things appear to be gray to them. And you might have even talked to people that didn't really know that they had a color blindness, but maybe you picked up on it because they kept saying something like, oh, that looks really gray, you know, or like, hey, look at that pretty blue house. Oh, it looks kind of gray to me. So because we all perceive color differently, it really is just a perception in our mind. It's a trick, an illusion that our brains are playing on us. And the reason why that happens is because the cones in our eyes, we have cones and we have rods. Cones perceive color, rods perceive black and white or contrast. And those cones, sometimes they can be damaged, or some people are born with cones that malfunction a little bit, and they're roughly equivalent to red, green, and blue. They get stimulated by that red, green, and blue light. And so if I have a cone that's damaged that cannot really pick up blue, and I'm looking at this marker, I don't see blue. I don't really have a perception of what blue even is, right? So just think about that. If you have normal color vision, or at least you think you have normal color vision, and you think to yourself that what I said was BS, that if I turn the lights off, that this is no longer blue. Well, just think about the fact that what if you didn't have the blue cone to perceive blue in the first place? This never would have been blue to you. Therefore, even though I see it as blue, and maybe you see it as blue right now, someone with, the cone or a deficiency where they can't see blue, it never was blue to begin with. Now, does it make more sense, maybe, that this is not blue necessarily? It's just that we perceive it as blue because of the light rays that are hitting it and bouncing back to us. So keep that as your basis, your fundamental understanding of color, that it's a trick being played in our minds.